Hello there, welcome back to our channel. And this time we are going to analyze the performance of a feedback amplifier. So as you can see in this circuit, I have an input signal, and that input signal could be a voltage or current. I have an output signal. That output signal can be voltage or current. There is an amplifier with an open loop gain called as AOL. So this is open loop gain. What is open loop gain? It is the gain when I don't have any feedback into the circuit. Okay, so that is when I say there is an open loop gain. However, if I say I want to feed a portion of the output back to the input, and by means of some network that is labeled as beta. So this is the feedback factor. Actually, feedback factor is beta. So you see that I sense the output here, whether current or voltage, and feed it back to the input side, and this is called as error amplifier or it is also called as which is a difference amplifier or differential amplifier, which basically subtract the output. That's why there is a negative sign, and I'm calling it as a negative feedback. So it subtract kind of output signal, portion of an output signal from the input signal, and the error is generated at the output of this error amplifier or subtractor, which is then amplified again by the amplifier. And this process continues until analyze the output of the error amplifier is 0 and there is nothing to amplify. So there is one more parameter is called as loop gain, which is the product of beta times AOL, and the closed loop gain is called as ACL. This is closed loop gain. It means it is the gain now when I have a feedback into the circuit. So I can use the resistor or combination of resistor and other passives to form this feedback network, and so that I have a negative feedback in the circuit. And when that happens, I have to define the ratio of output divided by the input, which is the V out divided by V in. Okay, or let's say VID, which is the differential input in the case of differential amplifier. And I would let me write it here. So here, that is the signal V in, and it is written in terms of open loop gain 1 plus beta times AOL. So if AOL is very, very greater than 1, I can write ACL to be equal to AOL divided by beta times AOL, which is approximately 1 over beta. So if I have a larger feedback factor, that is beta is large, my ACL will be smaller and vice versa. Okay, and in amplifiers, we use the negative feedback to enhance its performance. So those performance enhancement can be seen in terms of improving the linearity of the amplifier at the expense of reduced gain. So here I will say the pros of the feedback amplifier and the cons of employing the feedback. So reduced gain. The second is your bandwidth is going to be up. Okay, the gain here is down. The bandwidth is going to be up. So for example, look at this figure. I have a Bode plot. This is a Bode plot. which is basically telling me the frequency response of an amplifier or a filter or whatever circuit I have designed using negative feedback, where the blue line is the response of a circuit without a feedback, and the brown line is the response of a circuit with a feedback. So here is the gain versus frequency. On the y-axis, I have a gain. On the x-axis, I have a frequency starting from DC to 1 into the power 10 hertz. And the gain is starting from about 0 here, 1 into 10 to the power 1, that is actually, and this is from -1. Okay, and this is 1k, and this is like 100k. Okay, so we see that. So now look at the blue line. I have this first pole, that is this -3 dB point per decade, where the signal starts dropping at the rate of -20 dB per decade. And in fact, this is the 3 dB point, not the per decade. Let me just correct that. Yeah, so here is my 3 dB point, I would say, where this is the point, and this is the slope where I see that there is a drop of the signal from the at the rate of -20 dB per decade, actually. Okay, and then it starts dropping, and I have a constant gain as shown here up to the frequency 1 into 10 to the power 4. So that is 10 kilohertz. Now, if I employ the feedback, so gain has dropped to the value. Okay, and that's the difference between the gain drop. However, my frequency is improved. The frequency response has been improved. So now 3 dB point is here. You can see the brown line. Okay, and then again the slope is -20 dB per decade. Here is the slope. So from this point right here to this point, I have the frequency response change, and the frequency at which I have the first pole in the circuit is beyond 1 mega. So it's about 2 mega, or even maybe 10 mega, something like that, because then it is like 100 mega here. So it is like 20 mega here. Okay, so you see that the bandwidth has improved. Then you actually can say that input and output impedances, uh, goes up or down depending on what kind of feedback you have. Okay, so that's also the advantage. And then if you improve the linearity, I forgot to mention, you also improve the distortion problem in the circuit. Your circuit will not produce much distortion. However, the gain will be reduced. We have seen that in the case of transistor circuit. Now, what if the feedback is not properly maintained or achieved? So if, for example, this beta times AOL, which is the loop gain, is negative, the product of beta and AOL. So let me write here again, ACL is AOL divided by 1 plus beta AOL. And if beta times AOL is -1, right? So in that case, your ACL tends to infinity, right? Because this is -1 plus 1, so 0, and the ACL tends to infinity. So in this case, your circuit might oscillate. Not might, circuit will oscillate. Okay, so there is a Barkhausen, there is like Nyquist plot Barkhausen criteria for oscillation, where we say that the magnitude of beta time loop gain is greater than equal to 1 in order to achieve the oscillation. That is one of the stability criteria or oscillation criteria, in fact. And the stability criteria is that you have beta times AOL must not be equal to -1, okay, for amplifier to be stable. So I think we've just covered what is the negative feedback, the concept of negative feedback, what is an amplifier using it. So amplifier that uses a negative feedback is called as feedback amplifier, feedback amplifier. And we've seen that we have used the transistor circuit where we have this V plus, and then we use the BJT. And before that, let me show you the gain that we have used. For example, we use the resistor here. Let me draw the circuit again. So here is your V plus, that is a supply, and then you use the resistor. Then you have this transistor, that is NPN, and then you kind of set, let's say, the bias, whether depending on what kind of biasing method you use, collector to base bias or fixed bias or voltage division bias, etc., so that you maintain the VBE here that turns on the transistor, and then you take the output here. Here is the RC, and the gain of this circuit is a kind of GM times RC. And you see that this gain is sensitive to the transconductance parameter. If transconductance changes due to, for example, temperature, environmental condition, or due to manufacturing issues, the voltage gain is different. So what you do here, you improve the circuit by placing a kind of emitter degeneration resistor. So it is RE, and then again you have the same condition of setting the bias point of the transistor, which is, let's say, RB. Again, you maintain the VBE here and the kind of output you mention here, and then you have this RE, and then there is a voltage drop across it, VE. So the gain of this circuit is purely set by the ratio of RC over RE, which is independent of the transconductance parameter here. And there is a negative feedback here uh, that we see, because of which we have the bias stability in the circuit, and how that can be achieved. So for example, let's say your transconductance of this transistor Q changes due to temperature variation. With that, your GM, which is, let's say, GM is given as the DC current IC divided by VT, which is the VT is the thermal voltage. At room temperature, it is 25 millivolt, and the IC will then change. So if, because of the GM changes, okay, so VT is fixed. So let's say you have IC that is changing, therefore the IE here will change, and therefore the VE, which is the drop across RE, will change. So depending on IC goes up or down, IE will go up and down, and hence the VE, and VE is basically VI minus VBE. So, and the VBE here would be VE minus VI minus VE, actually. Okay, so, oh, just a second here. I think we are making a mistake to explain the things. So the voltage drop across RE will, the current actually IE will change because the IC changes. And then IE, we know that is IB plus IC. And therefore, IB is equal to IE minus IC, right? So IB will change then. Yes. Let me explain again. So if there is a change in IC, there is a change in voltage drop across VE, because the IE will change here. So VE changes, it means the this voltage at the base will also change to maintain the constant VBE and again regulate the current IC into the circuit. So kind of negative feedback we see there. Okay. So hope you understand this video. We'll explore more concept of feedback amplifier as we move ahead. Till then, wish you happy learning.